So I'm just going to be going through the homework solutions for week 8, which was the searching and sorting week. So we have 3 questions this week and I've copied them in here. So we'll start with question 1. So question 1 is, write a Python function to implement the following algorithm for insertion sort. So here we just have some pseudocode. I know it's not indented properly, but kind of get a bit of an idea what's going on here. And then it just tells you a little bit about the arguments that it's going to need. So just a quick reminder, insertion sort, I have the answer here, and I have a little commented out what the solution will look like kind of step by step. So insertion sort starts with an unsorted list, and obviously sorts the list, and it basically creates a small sorted list on the left hand side and takes an element from the right hand side and inserts it into its correct position in the smaller sorted list over here. So I'll just talk you through the code. So starting here, we want to get the length of the list because obviously we want to know if we've gone too far. And the first thing we're going to do is we're going to check if the list has 0 or 1 elements. So if it has 0 or 1 elements that is already sorted, you can't sort a list of 0 elements, you can't sort a list of 1 element. So we're going to say, okay, return the list, it's already sorted. I don't know what you want me to do. But considering it has 2 or more elements, we're going to go into this block of code here. So we're going to say for I in range 1n. So basically we want to iterate over the list starting from the second element. So we're going to take this element as sorted because it's just 1 element. And then we're going to take this element, the second one, and we're going to say, okay, is it smaller than this element? And if it is, put it in front. And if it's not, then just stop. So here we say key is equal to input list I. So we're taking the index that we're on right now, which is the second one, and we're going to save whatever's at that position in the list to key. So here we would say, okay, I want to save 2 into key. So perfect, we have 2. And then we say j is equal to I minus 1. So j is equal to I minus 1 says, okay, so our index that we're at right now, I want to get the index before it. So j is just an index before it. So I minus 1, 1 minus 1 is 0. So the index we're going to be checking is 0. So we're going to be checking this element against element at 0. So we're going to say while j is greater or equal to 0 and key is less than input list j. So this is a little bit confusing. So what we're saying is while j is greater or equal to 0. So we're going to say while we're not checking an index that doesn't exist on the list. So while we're not checking an index that's like minus 1, that's gone off the end of the list here. So we want to make sure that we're not checking an imaginary element over here. And key is less than input list j. So we're going to say and if this element is less than this element. So if both those things are true, if we're checking an element that's definitely not gone off the end of the list and this element is smaller than, then what we want to do is we want to overwrite the element. So I have this written out here. So here we say, okay, are we checking a real element? Yes, we're checking index number 0, which is not less than 0. And is 2 less than 9? Yes, 2 is less than 9. So what we want to do is we want to take whatever's at this index and copy it over to where 2 was. So that's basically what this line here is doing. So our list will look like 99875. And now you might be thinking, but what have we done with the 2? But remember, we saved the 2 from earlier. So what happened is then we minus 1 from j to check if there's any other elements going this way, which will obviously stop the while loop because 0 minus 1 is minus 1, and that will say, minus 1 is not greater than 0, so that will stop. So then we come down to this line, and this line will say input list j plus 1 is equal to key. So we'll say, okay, we've gone too far. We need to step back 1 index, so that's the plus 1. We need to step back 1 index and make it equal to the key. So here we're saying, okay, we've gone too far, step back, and I want you to make that index equal to the key because that's where it's supposed to go. So basically what we've done here is we've checked these 2 items, we've copied that one over, check if there's any more items, and then because there are no more items, we can say, okay, this is the position that it must go in. So I'll just give you another example. I think it's down here in the list, just so you can have another example of how it might look with multiple comparisons. So here, as you can see in this stage of the list, we have sorted everything except for the 5. So our last element we need to sort is the 5. So we start at the 5, we save that into key, and then we get j. So j would be I minus 1, so that would be this index here. So okay, we're going to compare against this index. And then we're saying, okay, are we checking a correct index? Yes. Is key less than input list j? Yeah. 5 is less than 9, so that's correct. So we're going to copy 9 over here. So it would look like 2, 7, 8, 9, 9. And then we say j minus equal to 1. So now we're checking this index, and we start again. So we say, okay, are we checking a real index? Yes, we are. Is 5 less than 8? Yes, it is. So now we copy 8 into this index. So it would look like 2, 7, 8, 8, 9. And we repeat this again for 7, because 7 is also less than, 5 is also less than 7, and it also is not an imaginary index, that's an incorrect index. So then we would say it would look like 2, 7, 7, 8, 9. And then we get to 2, and 2 is obviously not, although we haven't gone to an imaginary index, we have found a number that is smaller than 5. So we say, okay, we've gone to 2, that's not right. We can't put it in there. We can't copy it over. So what we're going to do is we're going to go back 1 and we're going to copy in the 5. And then we go back and we copy in the 5 and we get our 2, 5, 7, 8, 9. And then we get our sorted list. I hope that's clear enough. It is a bit confusing, even though it's a small bit of code. But yep, this is the solution. And then question 2 is the binary search algorithm. So binary search is a very efficient way of searching. Excuse me. So 2 things you take in a binary search, because obviously we're searching for something, we also need to input the target. So we take in the list and we take in what we're looking for. So first off, get the length of the list, always a good thing to do to make sure we know what we're dealing with. Here we just have a little check, checking if it's not, the length of the list isn't 1 or 0, because obviously if it's 0, it's not going to be there. If it's 1, it's either there or it's not. You only have to check one element, but assuming that it's not 1 or 0 in length, we now do this little piece of code here. So it looks a bit bigger because I've commented it quite a bit, but it is actually quite a small amount of code. So basically what we want to do is we want to get the high and the low. You can also call these the start and the end. So you want to get the high, and these will both be indexes. So in the indexes in the list, so you want your high to be n minus 1, which is the length of the list minus 1. Because of course, if you have a list of length 5, the last index will be 4. So you want to minus 1 to make sure we're getting the very last index. So this will hold the last index, and then low will be 0, which will hold the first index. So while low is less than high, I'll get back to why they might be equal or might not be, low might not be less than high in a second. That's just basically while we're checking the list. Mid is equal to low plus high divided by 2. So we want to get the middle point. So we want to say, okay, what is the middle index? And that's just basically the way of saying, get the middle index. This is integer division. So what it will do is it won't give us a decimal point, because obviously we don't want our middle index to be 5.5 because that's not an index. We want it to just be 5. So the integer division says, I don't care about fractions, just give me a whole number. So now we have the end of the list, the start of the list, and the middle point. So we want to say, okay, what is at the middle of the list? Now, a very important thing for binary search is that your list is sorted, because this will not work unless your list is sorted, because we are assuming that when we check the middle item, everything on the left of the middle item will be smaller, and everything on the right of the middle item will be bigger. Or something along those lines. So we first check, so we save what is in the middle of the list into found. For example, that could be 3, 5, anything. And then we say, okay, are we looking for 3? Are we looking for 5? Did we find it? And then if we do, we can just return it, say, yep, we found it, first go, look at us go. But if we didn't, we say, okay, is the target greater than the one that we found? So let's say, for example, we have a list 1, 2, 3, 4, 5, and we've started on 3 and we're looking for 4. We say, okay, is 4 greater than 3? Yes, it is. So what we want to do, we know now that our thing that we're looking for is on the right hand side of the middle. So it's on the right half. So I want to say, okay, we don't need to check anything to the left of the middle point because we know that it's greater than the one that we're on right now. So we can only now check that section on the list. So what we want to do here is we say low is equal to mid plus 1. So what we're saying is, okay, the start of our list is no longer the start of our list. It's now the middle index plus 1. Because we obviously already checked the middle index. We don't want to check that one again. So we're just moving where we're checking our list to the middle plus 1, saying I only now want to check from the middle to the end of the list. And that's it. And once we do that, we will loop back around again and say, okay, now I'll explain the while low is equal to high. So because we keep shortening and halving our list, then we'll get to a point where low and high might be equal or might collide, because we keep halving and halving and halving until we get down to one element. And then when we get down to one element, it's either in the list or it's not. And then at that point, we can either return the element or we return none. So yeah, and then we also have an else here, for example, if the target was in the lower half. For example, if we had 1, 2, 3, 4, 5, and we found the middle one, which was 3, and we were looking for 1, we would say, okay, we know that it's less than, we can throw away the entire upper half of the list, and now we're going to move the high. So we're going to move basically the end pointer to mid -1, because we're saying, okay, I don't want to check from the start of the list to the very end. I only want to check from the start of the list to basically the middle. And then this will loop around again. So for example, let's go back to my 1, 2, 3, 4, 5. If we were searching for 4, we'd go around again. We'd get a new midpoint now. So our new midpoint would be low plus high divided by 2. So that index might be, instead of our index being 2, it might be 3 or 4. And then we get that, that number, do the same thing, reduce the list down, either moving the low or the high pointer all the way round and round, and then we should eventually end up with basically one element. And then, assuming we didn't find it along the way, we should end up with one element. And then if we end up with one element, we basically just check, okay, is it the element? If it's not, low and high will then basically collide, because you can't shorten the list anymore, and we will return none and say, I'm sorry, I checked the whole list, it's not there. So that's basically binary search. It's a very efficient way of searching, even though the code is a bit more confusing, but it runs very fast. And then question 3, very simple. You're basically just running both functions. So it said to pass an unsorted array with 10 random elements to the sort function, and then pass a sorted array to binary search function along with the element that you want to find, and print the index of the element from the array. So here, 2 ways you could do that. I just did a little code here on importing random, just to randomly generate 10 numbers and append them to a list. You can also just make your own list and just randomly make your own list. And then what you want to do is you want to say, okay, I'm going to sort the list using insertion search, and I'm going to pass in my list, whether you made it like this or like this. And then I just printed that. And then down here, okay. And then down here, we want to take the sorted list from our insertion sort. So this will produce a sorted list in here. And we want to take that and we want to pass it into binary search along with something we want to look for. So I'll just run that there. Yep. So you can see it's sorting the search, and then we get 1 because we're looking for number 5, and it's at index number 1. So that's all working perfectly there. I hope that all makes sense for you guys. It's a little bit confusing, but I'll just show the code one more time just in case I want to copy it down. Yeah, very similar to the pseudocode. And yeah, that is all the questions.